Well, hi, my name is Amir-massoud Farahmand, and I'm going to teach this course on reinforcement learning, Introduction to RL. Okay, so this is a course on reinforcement learning. And this is going to be kind of mostly a lecture-based course. So the plan is to have several lectures covering the basics of RL. Okay, so what is reinforcement learning? So at a very high level, suppose we have an agent. It can be a robot, or it can be any other kind of decision-making system. This robot or this agent observes the world through different sensors. For example, it has cameras for the robot, but say if the agent is a, say, smart air conditioning system, the sensors would be some sensors measuring the temperature of the room. After observing those measurements, it takes some actions or do some processing and take some action. And as a result, it states changes in the board. So say, for example, the robot moves, as you can see here. And what is the goal? The goal here is to achieve some kind of long-term reward. So I guess the slide should be changed, but the goal is to achieve some kind of long-term reward. So this is reinforcement learning at a very high level and abstract form. And you heard a lot about reinforcement learning in news, a lot of success stories, like several years ago, an agent could learn to play a game like Atari just by taking input from, say, image, essentially, and getting some score, basically measuring the score of the game. The other is that like AlphaGo playing, learn how to play the game of Go. So these are some kind of the success stories. Most of them have been on kind of simulations and games, but there are a lot of also potential or actual applications of reinforcement learning too. So for example, okay, let's see. Okay, so I mean, I talked about the games. So there are some Atari and Go. I talked about that. But say, for example, air conditioning systems. So how to make an air conditioning system that make people more comfortable in their buildings. Or for example, in the healthcare, how we can use a kind of reinforcement learning agent in order to help us prescribe or help us give us better treatments to a patient, especially a patient who has a, say, kind of chronic disease. So these are some applications that people have worked on it. I mean, they're not necessarily at the level of products, but they are some research. And of course, a lot of applications of reinforcement learning in robotics. It seems to be very natural to talk about reinforcement learning in context with applications in RL, and I guess many others. So in finance and other things. So there are a lot of applications. And so what is this course about? This course is about reinforcement learning and sequential decision-making under uncertainty. And the emphasis of the course will be on mostly the theoretical understanding. So we want to go step by step, try to understand why, what are the basic foundations and why, say, an algorithm should work the way it does. So this, I think this course will be more on the theory side. So you will do some kind of programming assignments, so you have some kind of practice with RL agents, but a lot of course material would be on, like the lectures will be on the theory side, and also your assignments, I will talk about that later, will be like proving things and deriving things and things like that. Okay, so this is the course. So let's talk about okay, so one thing that is, I think, so let's just build it step by step. Maybe we can start from reinforcement learning as a problem and reinforcement learning as a bunch of methods. So people refer it, like sometimes they say that, oh, that problem is a reinforcement learning problem. Sometimes they would say that, let's use a RL method to solve this problem. So I guess it's good to distinguish between them. Like as a problem, reinforcement learning is that how we want to act in order to some notion of long-term performance is maximized. So this is as a problem. And what I described like a few slides ago, it was describing reinforcement learning problem. But then we have methods of solving reinforcement learning problems, which basically we try to address that what kind of computation does an agent need to do in order to ensure that its actions lead to a good or optimal long-term performance. So these are the methods. One thing I guess that might be interesting, so I have this kind of okay, so I still need to figure out how to work with this iPad. Okay. So historically, I mean, there are a lot of computational methods that people use or can use to solve reinforcement learning methods. But historically, only a subset of all those methods are known as reinforcement learning methods. So for example, you can use evolutionary algorithms like genetic algorithms to solve problems that look like a reinforcement learning problem. But usually in the RL community, we don't recognize them as a RL method. On the other hand, when we talk about something like, say, Q-learning, that's of course an RL method. So this kind of distinction is a bit historical. Of course, there are some reasons why they say these methods are more suitable or more closer to the spirit of being RL methods. But this is somehow arbitrary. And I guess in the past several years, at least people recognize like evolutionary methods can also be used to solve RL problems. And it's acceptable in RL community too. Okay, so I am seeing some notifications. Let me try to figure out what that's, okay, so it's going something in the chat going on, so. Okay, so, right. Okay, so I guess I see some questions which seems to be addressed. Okay, so I guess I'm not very good in multitasking to go back and forth very fast, but yes, there is a course, slides should be on the webpage. There is a talks of increasing the capacity of the course, but I'm not 100% sure. So, okay. When usually we want to talk about reinforcement learning, we usually talk about agent and environment interaction. So we usually talk about an agent, so this one, and the environment, which is basically whatever it's outside the agent. And then we talk about concepts like state, reward, and action. So let's basically go through it. I go through it a few times gradually with more level of detail or also mathematical precision. So this is a kind of abstract diagram that describes how an agent and environment interacts. So how does it work? There is an agent. This agent observes something from the environment, essentially the state of itself in the environment. So for example, it can be location. If it's a robot, it would be a location of the robot in the environment. And then it does some processing and generates some action according to something that is called policy, pi. We will use pi to denote this policy. So pi is, it's a function, it's a mapping. And the action is the result of that processing. So this action goes to the environments. And then, so for example, for a robot, it would be a command to move forward, say. And then the state of the agent changes in the environment. So it goes from x of t to x of t plus 1. And it does it according to some essentially dynamics, P, that I'm showing you with P here. And also it receives something called reward, R of t, which basically, roughly speaking, says that how good that action was at that specific state. And then this information, next state and R reward, goes to the agent, and the agent chooses another action for the time step t plus 1. So this is a kind of general framework or general kind of diagram to talk about this. So let's go through it a little bit in more detail. So one is that, okay, so what is agent? So agent is essentially a decision maker or the learner. So it can be a robot, or it can be a medical diagnosis system, or it can be air conditioning system. So we usually want to kind of refer to the kind of the mind of this interaction as the agents and not necessarily the physical system. So when I talk about robots, it is not necessarily the physical robot, but the part that makes the decision making. And so the other part is the environment, which is anything that is outside the agent, which agent or kind of the mind of agent interacts with it. So it would be physical world outside the robot. So here I mentioned outside the robot, but I mean, if you want to be a bit more precise, you can even consider the physical body of the robot part of that in the environment. Or patient's body in the case of a medical diagnosis system, and diagnosis and treatment. So it is interacting with the patient. So how the patient changes if you give specific, say, antibiotics to him or her. And for air conditioning system, it would be the room. So the environment would be the room, and basically we want to see how it, like the temperature of the room changes, and that would be kind of the part of the state of the system. Okay, so let's see how agents kind of interacts. I described it like visually, but it can be a bit more formal. So at time t, agents at time t equal 1, 2, 3, probably up to infinity, the agent observes its state. Okay, so it observes its state. And what is state? State is kind of, as I mentioned, like position of the robot or vital information of the patient. More generally or more accurately, state is essentially a variable that summarizes whatever has happened, or it contains all the information that agent needs to know. So I will have more description of it, or more kind of basic explanation of what it is in some lecture notes that I will post. But we can think of it as currently as some variable that summarizes whatever has happened to the agent so far. And that's all the information that agent needs to know about its state in the environment. So the agent also picks an action AT. And this is according to policy. Sometimes we use A of t is equal to pi of xt, for example. So basically this shows that it's a function of xt, this is the action. Or policy might be stochastic, which means that given xt, the policy generates a basically specified distribution of possible actions, and the agent picks one of those actions randomly. Okay, then the state of the agent in the environment changes and become xt plus 1 according to this transition probability kernel or distribution. So this would be the new state of the agent in the environment. And here I think what is important to notice is that the state or this dynamics depends on two things. One is that xt, and the other is at. So it depends on what state it has been and what action it takes. It doesn't depend on anything else. And also the agent receives some reward, which depends again on xt and at. it could theory also, it could depend on the new state that it has been, but I think I will describe it later, that it doesn't matter. I mean, we could essentially have it like xt, at, and xt plus 1 instead of what I have here, but they are mathematically the same. So I guess throughout the course, I'm going to use the first formulation here. Okay, so let's see. So state, as I mentioned, is a kind of variable that summarizes whatever has happened to the agent so far. Policy is action selection mechanism. It's a mapping from states to action. It can be deterministic in this case, or it can be stochastic. And then the transition probability kernel or distribution describes the dynamics. So for example, if for a robot, it would be a set of electromechanical equation that describes the position of the robot, or for a patient, it's a dynamics of their body. It's a very complex dynamics. It's probably not very easy. It is not easy to describe by a set of equations, but there is some mechanism or dynamics, and that's what transition probability kernel basically describes. Okay, maybe one other thing is that is important is the reward. I mentioned it, but here reward is a kind of real valued number that specifies immediate desirability of the choice of action at state xt. So for example, if you have a robot successfully, and we want the robot to go to some location and pick up some object, so we give a positive reward if the robot achieves that. And if, for example, it breaks that object, that would be a negative reward. So it would be actually a punishment, but we talk about negative reward. Or if the patient has had infection, but then based on the action that we give, for example, the antibiotics, the patient doesn't have infection anymore, so that's a positive reward. Or in an air conditioning system, if the room's temperature becomes comfortable, then that's possibly a positive reward that kind of the occupant of the room would say that, well, it's comfortable, so that's good, so it's a positive reward. So one remark, I guess, that is important here is that, so here, what is important is, okay, so I guess that might be better, is reward essentially encodes how desirable or valuable that certain action at that state has been, just based on kind of the immediate consideration. So at that moment, whether it is good or not, but it's not necessarily mean how desirable that action, that state is from the long-term perspective. So what would be an example? So for example, if I eat a cake, well, that's tasty, so that's desirable. But if my goal is to lose weight, that's not a good action in the long term. Or in financial, kind of a financial example, if I want to save money, if I spend something and buy a new gadget, that's good, probably make me happy for a day or two. But if I have a kind of goal of saving money, that's not a good action. So still, I get a high reward for buying that gadget, but in the long run, I'm not doing the right choice. So, and we get back to this later because reinforcement learning is all about how to think about long-term effect of actions and how to choose actions in order to maximize that long-term performance. Okay, so is there any questions so far? Let me try to see. So there's a quick. Okay. Okay. Can you make the slides a bit smaller? So is it better when I move that? Okay, it looks good now. Okay, so I think it would be better if, I mean, it's kind of strange to talk, not being a real classroom and presenting through through Zoom, but it's good to try to make it a bit more interactive. Don't feel shy.
I just didn't want to interrupt, but thanks. It looks good now. Thanks.
So any question about RL or what I've described so far? Everything is clear? Okay, so maybe one exercise we can do, I don't know if you have enough time or not, but is like think of some application that you are doing, especially if you're on the application side. If you're working on robotics or healthcare or anything, I mean, there are millions of applications. And think about what application, in your application, do you have an RL problem? Like, do you have any essential problem that has this sequential nature, that there is some concept of agent that interacts with something else, and then it wants to maximize or minimize something.
So Amir.
Yes, please.
Yeah, hi. From an application side, I can think of like, for example, the financial market as a prototype of this kind of sequential decision-making and maximizing prototype, but it's not really talked about in the ML domain because the negative connotation, if I may, associated with finance and whatnot. But yeah, I mean, like, I don't know, I mean, when you talk about, if you as an application, that would be a good example that I can think of, like, you know, just that's sequential decision-making, right?
Yeah.
But, anyway.
Yeah, I agree. I mean, financial example, if you want to kind of trade in stock, so stock market, that makes sense. Like your actions would be what to trade. And you don't only care about what happens tomorrow, but you want to become rich in a year or 10 years or something like that. So your horizon is longer. So I guess that's a good example. And I think actually people have, I mean, tried to several times to apply RL type methods in financial problems. Any other?
I have a question. So in RL, so like in healthcare, if you don't know equations, like how the physiology changes, how can it solve it? Like, can it solve it efficiently compared to other solutions?
So I guess you're talking about, I hear two things. One is that if we don't know the equations, and the other is that how it can solve efficiently, right? So,
right.
Okay, so let me answer both of them. I mean, it will become more clear later, but here we don't assume we know, in RL, we don't assume that we know the equations. Like here, when I'm having this dynamics, or yeah, I guess when I have this dynamics here, x of t, okay, so. Okay, so hopefully you see this kind of the dynamics. So this transition probability kernel, this is not something that the agent knows in RL, but it is only something that generates the data. So actually the kind of nice thing about RL is that we only assume that the agent receives the data in the form of like given xt and at, what would be the next x, essentially, x of t plus 1. In healthcare, that is very complex, how that data is generated, but it is generated because we have data from real people. So their body would be the simulator. So I guess that's a kind of the benefit of it. But also I should say that, I mean, at least the first few lectures, we assume, or at least one of the lectures, I guess third lecture. We assume that we know the model, and I talk about methods that given known model, how to solve the RL or how to solve this sequential decision-making problem. But I guess your second point was that how efficient it would be. So that's an interesting point, which basically it means that sometimes it takes a lot of data points, samples, or number of interactions with the word before the RL agent can learn how to perform well, like close to optimal or something. Say, for example, Atari games, it takes millions of samples, interactions, before the agent learns how to play Atari, which I don't know exactly how many hours it would be or how many days of gameplay would be, but that's a long time. It's not just after 5 minutes it figure out how to play it. And so it means the same in healthcare. It might take a lot of data. So maybe we need to have thousands of patients data in order for the agent to learn how to act properly. So this being said, I mean, much of RL research is essentially about designing agents and algorithms essentially, that are more sample efficient. Means that with fewer number of data points, we can learn better results and faster. So that's a kind of the research. So in any given application, I think you need to see what are the available methods are and what are the data requirements and things like that, and see whether RL might be a suitable solution here or not.
Thank you.
Okay, anything else? Okay, so let me continue. So here, okay, so here the process of interaction of agent, I described one cycle of it, but this process continues and agent receives a sequence of states, action, and reward. So X1, A1, R1, X2, A2, R2. And this sequence might terminate after a fixed number of time steps, like T equal to 10 or 100, or until the agent gets to a certain region of the state space. For example, a robot goes and pick up an object and successfully put it in the desired location, and that's the end of it. Or it might continue forever. So for example, if you have an agent that is supposed to live forever, or at least in theory, that sequence continues for a very, very long time. So I'm going to describe it a bit more formally, but essentially each of these cases, either fixed, we call it fixed time horizon problem. The other is that until agent gets to a certain region of the state space, we call it episodic problem. Or it might continue forever, we call it continuing problems. Okay, so let's try to formalize what I have said so far and kind of gradually become more familiar with notations and the mathematics. Okay, so some notation I'm trying to introduce. I'm going to use it, I think, regularly. So let's try to. Okay, so one is that, okay, for some given space omega, I use M of omega to denote the space of all probability distributions that can be defined on that space. And I use B of omega as a space of all bounded functions defined on omega. So just kind of make it more clear, suppose omega is this set of 1 to n, then M of omega, or M of 1 to n, would be the space of all probability distributions that essentially discrete probability distributions with n elements. Or if I define, say, omega equal to r, M of r would be the space of distributions on the real line. So Gaussian distribution, Laplace distribution, things like that. But I want to talk about all possible distributions. So this is just a notation. And the other is that B of R. Okay, so this should be without D. B of R would be the space of bounded functions on real line. So I guess I'm sure you're familiar with these all notations. So this is natural number, real number, and D-dimensional Euclidean space. And D can be a kind of number like 5 or 10 or 1,000. So these are some notations. Okay, so we have MDP, or Markov decision process. So what is MDP? So before maybe defining it, this is a kind of mathematical framework that allows us to talk about RL problem in a rigorous way. This is a very kind of commonly used framework to describe the kind of the math behind many of RL methods, but it is not the only one. And probably I will describe it later. Maybe I just mentioned that the name. So another framework is called partial observable MDP. And that's kind of a generalization of MDP. But for at least most of the course, or most of the theoretical work of the course, we work with this MDP framework. Okay, but what is MDP? Yeah, it's kind of, I have to figure out how this kind of app works. If I remove this, it doesn't write. So, okay, so MDP is a tuple. So it's a discounted MDP is a tuple defined by X, A, P, R, and gamma. So what is X? X is the some state space. So it's a measurable state space, but you can ignore the measurable part. So I just wrote the technical definition, but if you don't know much about measure theory, you can ignore any term related to measure on the slides or on the lecture notes. I try to kind of reduce the number of them, but this is kind of technical requirements. And A is the action space. P is the transition probability kernel. So, okay, so this is interesting. So let's try to understand it. This is P basically says that the input of it is X and A. So states, input it state space and action space together. And the output of it would be M of X. Recall from previous slide, M of some space omega is the space of all distributions on omega. So this would be the space of all distributions over a state space. So the form of P would be something like this. So we have state and action, and it provides a distribution over a state. So we can write something like this. So X prime is coming from distribution of P of P that is conditioned on X and A. So it's a conditional probability distribution. And the same for R, or similar for R, with the difference that here we have this space of distributions is over real lines, which basically what we want, because we want R to be a real valued number. So that's why the distribution is on real numbers. And it's called the immediate reward distribution. And then we have this kind of gamma, which is a number between 0 and 1 as a discount factor. So throughout this lecture, I'm going to actually talk about cases that are not necessarily discounted. So in that case, if it is not discounted, then we don't necessarily talk about gamma. Or we can talk about gamma equal to 1. It becomes more clear. But here the definition is for discounted MDPs. If it is not for discounted MDPs, we just remove the definition of gamma there. Okay, so.
Sorry, one question. So is the reward function stochastic or deterministic?
It can be stochastic.
So in that case, it is a reward distribution. Otherwise, it is just some deterministic
right.
values. Okay.
Yeah, it's not. It's in that sense, it's not function. So it's a reward signal that if you specify X and A, state and action, you get a random number that is your reward. But if you do it, if you're in the same state and action, you may get something, some different number. Yeah, I guess, but sometimes in many problems, we just think about reward function, and function would be special case of reward distribution. So, okay, so maybe I think I will have a comment on that. I mean, similar to what you said, here the transition probability kernel is a distribution. So when you are at state X, choose action A, you have a distribution over all possible next states. But then it is possible for some systems, for some dynamical systems, that you always get the same next state every time that you kind of run that system, which basically means that that system is deterministic. I think I have a note on it. That's why I will get to it later.
Thanks very much. So one more notational clarification. So
Sure.
when you are referring to the set of bounded functions, which is B omega, are you saying that the set of functions that maps from the space omega to a set of bounded values?
Yes,
is that the case, or?
That's right, yes.
Okay, thank you very much.
Yeah, it is defined an omega and two real valued number, but it doesn't take positive or negative infinity. Okay, any other question? Okay, so here, I guess I kind of repeat what I said before a bit more mathematically. So essentially, MDPs encodes the temporal evolution of a discrete time stochastic process that is controlled by an agent. So the agent, in the beginning of this stochastic process, where we index it by time t, suppose the time starts at time 1. So x of 1 is coming from some distribution, rho, and rho is a distribution over a state space. So that's why I use m of x there. Here, rho is not a definition within the definition of MDP. So that's, you don't see rho in the previous slide. But just when I want to describe this interaction of the agent, I basically mention how it starts choosing its states. Agent chooses some action in some way. Agent goes to the next states, xt plus 1, according to this dynamics, and receives a reward. And then this process repeats, and the trajectory would be x1, a1, r1, x2, a2, r2. And in general, this trajectory is random. If P and R, and also the action selection mechanism, if they have a random part in it. Yeah, so I guess that's, is this clear?
Yes.
Perfect. Okay, so I guess I have a remark that usually, well, not usually, but sometimes you see that the reward distribution also, we say that reward also depends on the next state that the agent goes. So it depends on next state, xt plus 1. In that case, we would have a, but these two cases are kind of mathematically the same. And here it shows why it is the case. Maybe I skip it. You can take a look at it and see if it makes sense to you or not. But that's the, they're mathematically the same, but so I use the notation that reward only depends on xt and at instead of xt plus 1. And kind of the proof is that if we have one distributed reward kernel, R prime, that depends on xt, at, and xt plus 1, we can define a reward kernel R that only depends on X and A by kind of like marginalizing through the dynamics. So it would be like, if we take this integral, we get from R prime, we get R. Okay, so Markov decision process is a kind of quite a general framework. It allows.
Sorry, a question.
Sure.
So in nature, agents that evolve have like usually conflicting and competing reward systems. So is there a such modeling for like decision processes? So are we always looking at like singular scalar reward measures?
Yeah, that's a good point, and I don't talk about it much here. No, here the assumption is we only have one reward function or reward distribution, and they're not conflicting. And kind of, at least some people believe that you can always convert a multi-objective reward scenario to a single objective one by kind of tuning how the relative importance of them. That being said, there are frameworks like MDPs, but with more than one reward objective, essentially multi-objective MDPs. People have done research on that. So they exist, but I don't talk about them. But actually that's a good point. Like, well, that's a good point because of itself, but also one, I guess, important question is that how do we get reward in general? Like, who specified reward function or reward distribution? So I think I will maybe talk a little bit about it at some point, but here the assumption is that reward is given. And kind of the idea is that the designer of the system has designed a reward function. So for example, for robot, she has specified what is a good action, what is a bad action, or bad state action, essentially. But in general, like for animals.
Many times in like evolutionary systems, rewards themselves evolve.
That's right. I mean, rewards, I guess, for in agents that are alive, the reward, if they have a kind of complex enough brain, the reward system essentially has been evolved so that it increases their chance of survival. So this is interesting because people also try to evolve reward system for RL agents too. So kind of bringing ideas from how evolution works and how it specifies the reward system, that has also been explored. But probably I won't talk about it much, or maybe at the end, maybe we'll read a paper about it.
Thanks.
Okay. Okay, so about the MDP. Okay, so it's a general framework because it kind of gives us flexibility in choice of, say, for example, state space. State space can be finite. So X can be like X1, X2 to Xn, and n being a finite number. Or it can be infinite but countable, like X would be like the natural numbers. So, or it can be continuous. And by continuous, I mean a subset of real line or Euclidean space. Like here, it's RD, a subset of d-dimensional Euclidean space. Or it can be many other spaces too. So I guess that's one thing. I guess the same thing for actions, like actions can be finite or actions can be also continuous. And when we talk about, so maybe this is kind of notational thing or kind of terminology thing, that when we talk about finite MDPs, we are referring to MDPs that have finite number of states and actions. When we talk about continuous, we are referring to at least the state space is continuous, action space might be finite, or it might be continuous too. And I guess the use of continuous is not completely accurate. but that's how people use. Like whenever real numbers comes into the picture as a part of state or action, we call it continuous MDP. The other thing is about the dynamics. The dynamic can be stochastic or deterministic. So the framework is described for stochastic dynamics, but deterministic dynamics basically is a special case of stochastic one. So what is a deterministic dynamics? Deterministic dynamics intuitively, if you're, okay, so intuitively it means that if you're at one state, you choose one action, the next state would always be the same. So if you are from, say, control engineering background, or taken a control theory course, that's a usually the most commonly used type of dynamics that people write. So for example, we have something like, say, for linear dynamical systems, we have xt plus 1 would be matrix A times xt plus VUT. So this is the notation that people in control often use. And U here actually is RAT. So we use AT instead of UT. So, or another case would be more general for nonlinear dynamics. So xt plus 1 would be some function of xt and at. So this is deterministic, but not necessarily linear dynamical system. And we can always write this in the form of transition property kernel. So essentially what we require is that we define a distribution that has all the mass, or probability of equal 1 at the point that f of xt and at is suggested. Is this clear? Let's see. Is there any questions? So R, there was, I guess, comment about that R, whether R is expected reward. R is, like, I think, if you're referring to this R, that's a distribution of reward, not expected reward. So I'm going to talk about it. We will introduce an expected reward later, but this is a distribution. So think of it as a Gaussian distribution and this kind of notation for it.
Oh, sorry, I was referring to the R in the box. I think that's the expectation over the next state, where where we convert the R prime into R.
Oh, this part? Which part?
Yes, yes. Yeah, the remark, yes, yes.
Okay, so here R prime and R, both of them are, right, I mean, but this is still both R and R prime, both of them are distribution. I'm just marginalizing one of them. Right here, I'm marginalizing X prime of this distribution R prime. Like you see, I have X prime marginalizing through the dynamics to get another distribution. So I'm kind of computing some expectation in some sense, but this is still this is a distribution.
Yes, yes.
Okay, so one other thing, this is a definition of a policy. Kind of start with a very general definition, so you know that, but later we get to a definition that or the use that I described when I talked about in that figure several slides ago. Okay, so policy technically is a sequence of these functions. So I use pi bar, the sequence of pi 1, pi 2 to pi infinity, if it goes for infinity, such that for each time, so pi of t is giving a distribution over actions conditioned on whatever happened in the past, like x1, a1, up to xt minus 1, at minus 1, up to xt. So we have information, the sequence that we observe from the beginning to the current time, and we pass it through this kind of distribution or conditional distribution or pi t that gives us a distribution over actions. So this is a kind of stochastic kernel on actions. So it's the output of it would be a probability distribution over action space that satisfies kind of the laws of probability. Essentially, we want to say that pi of t of action space, the probability of it is 1. So this is, I mean, this looks kind of complicated, but it is simple. It says that we have information from the beginning of when agent starts working up to current time. Given all that information, I define a probability distribution. And because it's a probability distribution, the probability of the action space, the whole action space, should be 1. And it should be defined for all possible input sequence. So this is kind of like technical definition or kind of technical requirement that it should not be defined. Say, for example, if it wasn't well defined for some subset of sequences that the agent has observed, then that would not be a proper policy. So here, I guess what is important here is that this policy depends on whatever happened from the beginning up to time t, and also policy is a function of t. So here, there's a t dependence here. So policy 1, pi 1, pi 2, and pi 100, they can be different in this general definition. But then, okay, so we get to an important case. Important special case is that when pi t is only parameterized by xt. So we have all this sequence, we can just ignore it. We only look at xt. So ignore whatever happened 5 times steps ago. If we can ignore it, then this policy is called a Markov policy. And as you see, I guess most of the results that I'm going to talk about in this course will be for this type of policies, Markov policies. So basically, these policies ignore whatever happened in the past and only look at the current state of the agents. Okay, so I guess the other definition is that whether the policy pi t assigns mass 1 to a single point in A, if like one of the actions has all the probability and the other actions have probability 0, then that pi bar is called a deterministic or non-randomized policy. And if it assigns a distribution over actions, which is not kind of concentrated in one particular state, it is called stochastic or random policy. So maybe, I can see if I can show you how it may look like. Say if it is actions and this is a policy conditional something. I mean, either all the past or just xt, depending on whether it's Markov or not. If the probability distribution looks like this, say, that green one, that's a stochastic policy because all actions have some probability. But if it has, say, so this kind of delta function, Dirac's delta function, which basically indicates that all the probabilities only concentrate at these points, and the rest have probability 0. If that's the case, then that would be a deterministic policy. So when we do that, we use a different notation when we refer to whether it's stochastic or deterministic. So we use pi of kind of dots condition on X to refer to a, okay, maybe I should mention some other thing too before that. Okay, so here you remember the policy depends on time. But if it doesn't depend on time, no matter whether the agent's at time step 1 or 10 or 1,000, then that policy is called stationary. So stationary policy is a policy, Markov policy in the form of pi, bar is pi, 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 pi. So when all of them is the same mapping, essentially, it's called a stationary policy. So we can have a combination of them. We can have a stationary policy that is Markov, or maybe it is not Markov. Or maybe it's a stationary policy that is Markov and it is stochastic, or it is deterministic. So when a policy is a stationary Markov policy, we usually use notation like this, pi of kind of point condition on X. And if it is deterministic, we use some notation like function as a mapping of pi of X. So that would be essentially our notation. Okay, so maybe we can have a few minutes of break and we start at almost 5 minutes. Now it's 2:04. Maybe start at 2:10. Does it sound good? Okay, so we start in a few minutes. Okay. So let's continue. Let me try polling. Okay, I haven't used this polling system of Zoom, but let's try it. Might make it a bit fun. So I just ask about your educational background. Yeah, I guess it makes sense. I mean, it's not super important. I just wanted to see how it works and also get an idea like who is enrolling in the course. Okay, yeah, let's try this. I believe. Okay, I guess it's good. We are 95%. Let's see. Share results. So I guess you can see the result, right? Oh, that's interesting. I mean, it's mostly computer science, mostly masters. I guess no undergrad from CS, apparently. So I imagine the class is full, so that's why. And others, so I guess I don't know who the others might be, but that's good. So yeah, I try sometimes to have something like this too. Might be fun or not. Okay. Okay, so so some more notations here. It's called basically this is called policy-induced transition kernel. We want to talk about the dynamics if the agent follows policy pi. So the idea is simple. So maybe just kind of define following as when a Markov stationary policy pi, or agent is following a Markov stationary policy pi, whenever its actions are selected according to that policy. So it would be either in this way, so AT would be pi of xt when it is the policy deterministic, or it would be stochastic. AT would be coming from a distribution of pi condition on xt. Okay, so then the policy pi induces two transition probability kernels, P of pi and P of pi. And so I guess the difference between them is one of them is from states, excuse me, to distribution over states. The other is state action to distribution over state action. So hopefully it becomes a bit more clear. So let's maybe start from the first one. For a subset of A, subset A of state space A, this is the definition. So what does it say? It says that probability P of pi of, if we start from state X and going to state A, when we are following policy pi, that's essentially that kernel. So we want to see if the agent starts from, say, 1 point and follows policy pi. I mean, there is a possibility of going to several states. So this state, what is the probability of going to this region? So that's all. So let's see how the definition, or how we can write it mathematically. So it is saying that this P, remember P depends on state and action. So state and action. How is the action selected? Action is selected according to policy pi. So with some probability, if we choose state X and then choose action according to policy pi, we go to state Y. And this is P of dy condition on X and pi. You can think of it as a density of going to that state. Okay, so which states we care about? Only those states, only those Y's that belong to sets A. So we have this I indicator function that is equal to 1 whenever this condition is true. So I of Y being in A, that is recounted by 1. If it is not true, then it would be 0. So let me see if I can draw something. So if, for example, yeah. So this is again, so for choosing some specific action, I may go to many other states. See, some of these regions are not within A. I only count the subset of them that are within A, and that would define this probability. And for the other one, it is very similar with the difference that here we condition on state X and A. And at the next state, B is of the form of, okay, subset B of state action. So it is like this, that we start with X and A, we go to Y, and then we check whether Y and pi of Y is within B or not. If it is, then we count 1. And by taking average, we get the probability of getting to that subset of state action B in the next state. So, I mean, this might look confusing. I mean, especially I guess the second one. The first one probably is more intuitive. But this is a kind of useful notation, like this notation of P of pi, that is kind of, we use it often. So I guess there's a small notational problem here, I noticed. So here, I use P of pi, which is different font of P of pi. They're supposed to be the same font. So shouldn't confuse you that I'm talking about two different things. Both of them are the same. Okay, so this is a policy-induced transition kernel, so we will use it. Okay, so I think this might be when we have a countable state action space, sometimes we use summation instead of integrals, because sometimes it is more clear what it means. And so the integral in the previous page, like this integral that we have here, if we write in form of summation, it would be essentially this, like this. It would be summation over y's. So p of getting to y conditional starting from state x and choosing action pi x, and then y being in set A. So that's the same. Also, if A is a particular choice of states. So if A is a some y, then of course from here we get that p of pi of getting to y condition on x can be written as p of y condition on x and pi of x. So I guess that's simple. One other thing that is, I guess, that there are maybe 2 points that I want to mention here. One is that here I talked about a policy that is deterministic. So I could substitute action with pi of some state. But if it is stochastic, we can have a similar definitions. Like the intuition, everything is the same. We just need to take integration with respect to all the possible actions that a stochastic policy might generate. The other one that I want to mention is that this is essentially P of pi is the distribution of starting from state X, following pi, and distribution over next state. We can talk about following this policy pi for 2 steps or 10 steps or m steps in general. And we can inductively define these notations essentially. So we get a notation like P of pi to the power of m, and that basically means that. And actually taking to power is not a kind of just a notation, because if we talk about finite state and action, and we can represent P with a matrix, or P of pi, we can represent it with a matrix, and the probability of going m step ahead with that policy would be the same as taking the matrix P of pi to the power of m. So in the finite state, it is kind of what we expect from linear algebra. So I think I will have definition of that in the lectures, the lecture notes, but I skip it here. Okay, is there any questions so far? Good.
So here, so in the equation in the right part, we see the sigma of y belong to x. So right. It means that it is over the whole x, not the A.
Right, yes, it would be over all state space, but here, this part of it basically counts whether y belongs to A or not. You could.
So if y belongs, if y belongs to A, then the py given x pi x is 1, and if it's not, it's 0.
P of y. So if y belongs to y, this would be equal to 1. Otherwise, it would be 0.
I see.
So this, I mean, I guess I understand what you're talking, and it would be essentially the same. So I could also write it. I think what you're thinking is the second formulation.
Yeah, that's much. Yeah.
So this is these are the same. So this is indicator function it becomes 0 or 1, and we just, we take summation over the whole state space, but we only become activated in the subset that is belong to A. So maybe in the finite case, this second formulation is more clear, but I find it in the integral case, this would be more clear. I mean, also I could probably change it to integral over subset of A and then remove these parts. But these are equivalent.
I see, thank you very much.
Okay, so let's talk about, okay, so we talk about the basics of MDP, some notations. Let's gradually get to the RL problem. So RL problem, remember, was the problem of how to act in order to maximize some notion of long-term performance. So the question that we have to think about is that how we can, what is the definition of long-term, first of all, and how we can quantify it. So I think I start with short-term first. Like what is, how to define performance if we only think about short-term performance, and then we get to the long-term later. So this is a immediate reward. I call it immediate reward problem. I mean, it is not a standard definition, but it's clear what I mean. Suppose at each round of interaction with its environment, so we have an agent, at each round, an agent starts at a random state x1 coming from some distribution rho. So you put the agent in one random point, and then agent chooses policy A1 at according to, chooses the action according to its policy. So A1 is pi of x1. Suppose it's a deterministic policy. And then it receives a reward R1, which depends on x1 and A1. And then this repeats again. So another random state independent from the previous state and action is selected, and this repeats many, many times. So each of these episodes or each of these rounds are called episodes. And here the episode lasts only one time step. It's like one state, one action, and then you get the reward, and then episode ends and we start a new episode. So how should this agent chooses its action in order to maximize its performance? And I guess maybe to answer that, we need to first talk about what performance means here. Okay, so let's think about it a little bit here. So how do you define performance? If you want to define performance, what do you define? What is meaningful performance here? Okay, let's see, there are some answers in chat.
Expected reward.
Okay, expected reward. That's good. What does it quantify, expected reward?
So on average, how much reward, or how much, yeah, on average, how much reward the agent gets?
Okay, yeah, that's a very reasonable choice. What else can we think about? Maybe I help you. What I mean, there are probably many different things that you can think about. Like let me guide you what I think might be interesting to think about. Suppose agent happens to be coming in state X, the same state X again and again. Suppose rho is always choosing the same one particular state all the time. And once we get a reward of, so state is always, let me, so rho is always, say x1 is always state x0, say. So this is always the case. And then we get a reward of, say, 1.5. in another episode, we get reward of minus 1.3. And then another time we get reward of 10, say. And another time 7, and then another minus 3. So we can compute the average of these. It would be some number. And that's what you said, like average reward or expected reward. So that number, that's a one measure of performance. But then suppose this agent runs the same thing. Okay, maybe a different number. And suppose it gets the same average. Probably they are not the same. I mean, most likely they are not the same, but suppose they are the same. Suppose these are the same. Okay, so expected average reward or average reward, they say that in these two cases, like policy 1, so say this is generated by policy 1, this is supposed generated by another policy. The performance of both of them are the same. How can we differentiate between these two cases? Like, what's the difference between these two sequences of rewards?
Variance.
Right, variance. So one of them is very high variance, the other is low variance. Can you think about a scenario or a performance measure that considers this?
Like number of steps. So how many steps it took to get the average?
Okay, so how many steps it takes to get the average? I mean, it is a sequence, like suppose it goes for a long time. So it gradually converges to the average. But maybe what you're saying is that how stable it is around its average, maybe.
I think mean square error combines bias and variance.
Okay, right. I mean, but what is the target? Like, what is mean squared error with respect to what?
Because their averages are the same, so it doesn't matter.
Right. Well, but I think, I mean, you said the right thing. I mean, okay, so the way I'm thinking about it is that these two sequences have the same average. If we define a performance measure as expected average, both policy pi 1 and policy pi 2 are the same. But for some applications, maybe we want to have more stable rewards. Like we prefer the second one because the variation is less. The first one, the variation is higher. So if it's a financial, like if we are investing in some stock markets, if we are not if we want to be a bit more conservative, probably want to kind of choose stocks that are have less variations. So in that context, we think about measures of performance that incorporates, say, something like variance into the picture as a part of the performance measure. So I'm not going to talk about those. Probably, I mean, for sure, for most of the lectures. Maybe at the end I talk about it a little bit or maybe not. But here, we usually focus on some form of average or expected reward. But I just want to mention, or I just kind of the reason I mentioned all these was that we could define performance measure to somehow incorporate some notion of variation of rewards that we get, or some notion of risk. Let's see, there's some comments. Okay, right, yeah, so maybe lower risk, less variance, yeah. Reward to variance, so yeah, I guess the ratio of reward to variance, I think that's a kind of one of the performance measures that people use in finance. I guess a Sharpe index maybe. The other temporal value of reward should be discounted as per the problem domain. Right, so that's okay, so that's a good point, but this is because the time step is only one. So we assume that there's no temp, like each episode is independent from the previous one. But we get to that temp discounting very soon. Is there any case that pi1 is better? I mean, if the expected reward is higher, yes, that would be better. I don't know, maybe, I mean, we have a 10 here, so it's quite, seems to be quite large. But sometimes maybe we want to have more variations and we can define it that way. So that's possible. Depends, essentially it depends what we want as an objective. But all these things, we are not going to talk about them very much, or almost at all. Okay, so that was the setting. We can talk, as you said, we can talk about average or expected reward that the agent receives within one episode as the measure of performance. Episode is here is one time step, so just average, just that value. What is average here? Average is over repeated interactions with the environment. So we have like at the top, we have at each round of interaction, we take average over all these rounds. So if we go 100 rounds or infinite number of rounds, that would be the expected reward. Okay, so if we define the performance in this way, answering the question of how the agent should act in order to maximize this notion of performance is easy. Let's define expected reward. So expected reward is, I use small letter r of x and a, and this is essential expectation of rewards condition on state being x and action being a. So essentially I have the reward distribution, I take its conditional expectation, condition, state and action. In order to maximize the expected reward, what is the best action we can do? The best action we can choose is at each state, we should choose action that maximizes that expected reward at that state and action. So maybe I call it A star. So this is the best or optimal action at state X in terms of expected reward. If we defined another performance measure, for example, if we brought variance into the picture, this action would not be necessarily the best action. So that's important. Optimal action for this performance measure. And then we can define optimal policy as a map from states to actions, state space to action space. And essentially we repeat the definition. So pi star, we usually use star to refer to optimal things. So pi star is the optimal policy, is argmax of r xa when argmax is over action space. So these are the same thing, of course. Okay, so here it's interesting because the optimal policy, so this optimal policy, it was easy to find, and it does not depend on initial distribution. Like here, even though the problem definition is set that choose state x1 according to row, the row does not appear in any of these calculations. Okay, so that's, I think, one. Okay, so this was a kind of very short-term case. Let's go to different interpretations of long-term performance measure. So here I defined a new setup, finite horizon task. I call it finite horizon task, and it's a kind of standard definition, so it's not made up. The agent interacts with the environment for fixed time horizon t that is 1 or larger than 1. So say t is equal to 10. So it is very similar to before. So at each round or episode, now we call them episode, the agent starts at x1 equal to rho, so as before. So initial state, sample from some distribution. It chooses action A1 according to policy pi. So this is for deterministic policy. We can define it for stochastic policy too. Then the agent goes to the next state, x2, according to pi, the transition probability kernel that is conditioned on random variable x1 and a1. So we get x2. So we didn't have it in the immediate reward case. We had it in kind of the first part when I was talking about MDPs and agent interaction with the word. Also, we get a reward here. And then this process repeats for many steps. For how many steps? Or t steps. So it's finite with a fixed t until we get the last state and last reward. So we get a sequence of rewards, R1 and R2, R capital T. And we want to convert these T values, T random values, to some performance measure. Now the question is that what is the right choice? Okay, so how do you define it? Like some ideas. Don't look at the next slide.
Expected discounted reward.
Okay, that's reasonable, but why do discounts? I mean, people who don't know discounting, I mean, you will see it in a few slides, but why do discounts?
Because it's easier for convergence analysis, I guess.
That's true in general for the continuum case, but for finite horizon case, it doesn't matter. Convergence would be all right if it's finite horizon. But that's one reason. So, okay, so that's a reasonable choice. Any other suggestion? Okay, let's see, there are some things in the chat. Okay, yes, so I guess there's a comment that discounting also helps with assigning weighting to newer rewards, right? So that's, we get to something like that, some intuition like that. Just a sum of rewards, yes. More uncertain in future episodes. I'm not sure what it means, but so here kind of we want to consider each episode the same, independent from each other. I mean, the performance measure can be across episodes, but we don't want to kind of differentiate much between episodes. Okay, so let's see. So these are some good comments and suggestions. Let's see some of the standard ones, which basically I guess you covered already. Okay, so the question is that how should we evaluate the performance of agent as a function of the reward sequence? A common choice is just compute the sum of the rewards, like R1 to RT, sum of it. And then we call this G of pi as the return of following policy pi. So this summation, we call it return. And note that because if the environment is stochastic, G of pi would be a random variable. So it changes between each episode. So here, I guess kind of the intuition is that it doesn't matter whether we get reward at the first time step or 5th time step or 100th time step. All of the rewards are the same. So we just take a sum all of them, and that would be our performance measure. Or and that would be called it return of following pi. So we use, I think, notation G pi in most cases. So that's one. Another choice I think was mentioned is to consider discounted sum of rewards. So this, given a discount factor, gamma, which is between 0 and 1, we can define the return as G of pi is reward R1 plus gamma times reward R2 plus gamma to the power of t minus 1 reward RT. So this basically means that we get, if gamma is smaller than 1, say 0.5, the reward that we get at first time step is more important than the reward that we get at second time step. And second time step is more important than 10th time step. Okay, so so basically, kind of intuitively, it means that the values that rewards that we get earlier is more important for us. And maybe some example would be that if you receive a cookie, you prefer to get the cookie today than tomorrow, and tomorrow is better than a week later. So I guess it has some financial interpretation too. It means it is related to inflation rate in kind of the economy. $1 today, if you have a positive inflation rate, you prefer to receive $1 or $1,000 today instead of $1,000 a year later, because your purchasing power is a bit lower next year. So if you want to get equivalent of $100,000 this year or today, next year, you need to get, I don't know, $1,050 instead. And that kind of ratio is related to the discounting factor. And I guess maybe another example is somehow probably related to marshmallow tests, which you have probably seen that small kids, you give them marshmallow and then how much they can wait. It probably you can interpret it as what is their discount factor, like whether they prefer immediate gratification, have one marshmallow now, or they can wait for 10 minutes and get 2 marshmallows later. I don't know if it's actually like interpreted that way or not in psychology literature, but seems to be related. Okay, so another comment is that smaller values, okay, so I think it's clear that smaller values of gamma means that the agent is more myopic. And if it is closer to 1, it means that it weights future rewards almost the same as the current rewards. One remark here is that the discount factor is a part of the problem definition. So it is not necessarily a parameter that you optimize. The way that I describe it, it is essentially says that for this task, this is your discount factor because agent wants to be this much myopic or farsighted. Okay, so problem here is that the returns that I define, okay, so maybe I should mention that if discount factor here is equal to 1, we get the same formulation as here, right? This is equal to discount factor equal to 1. So there is a question, I think. Amine. So if you have a question, maybe you ask or, okay, maybe it was a mistake. So anyway, so the return that I define is a random variable. If you want to get something that is not random, like if the performance is not random, then we can compute its expectations. So here we take I have this return. This is the return, discounted return. I take expectation of it. And what kind of expectation? The expectation is that I'm saying that X1, the initial state that it starts, is state X. And then I follow policy pi. So that's the data generating process, or essentially action generating process. And then the dynamics of the environment says how X t plus 1 is generated. And I go for t steps and compute the return and take the expectation. Expectation would be over many, many episodes. And this is the expected value of these returns. This is called V of pi at state X. And this is called the value function of policy, V of pi. So essentially value function of a policy is how much we get the return if we, in expectation, if we condition on initial state being certain states. So this is the value function. And as you will see, we talk a lot about value function throughout the course. This is probably one of the most important kind of mathematical objects in MDPs and RL. So here I defined it for value function for a finite horizon problem for the discounted return. Okay, so let's see some comparison. Let's look at the case of t equal to 1 a bit closer, like the immediate, which is the same as the immediate reward case. So the value function v of x at state x is expectation of R1 condition on x. So if we compare it with what we had in the immediate reward maximization case, remember that we had R of x and a. That was essentially this conditional expectation. So here, what's the difference between these two terms? One is that here the expectation is only over x. Here the expectation is over x and a. Okay, so in V of pi, the choice of action is determined by the policy pi. So at state x, I choose action, or the agent chooses action A according to pi of x, or if it is stochastic policy, it chooses that way. So if we want to define something like expected reward that we had, but adding policy information into it, we can define it like this. So we define R of pi of state x as expectation of reward when initial states is x. So these are, remember, all for the case of t equal to 1. We just go one step and the episode ends. So here we see that if we define R of pi this way, this would be exactly the same as V of pi. Again, for t equal to 1. So essentially what I want to show here is that in the case of V of pi and t equal to 1, what's the relation between V of pi and expected reward? So expected reward was a bit different. It was conditional on both state and action. But if we define R of pi, it would be the same as V of pi. But then if we go beyond one step, t equal to 2 or 10, V of pi captures the long-term discounted average of rewards instead of just expected immediate reward that is captured by R of pi. So when t is larger than 1, they are different. Any questions so far? Okay. So let's see how to get the optimal policy. In the case, let's focus on t equal to 1 case. We knew how to, if we had to R of x and a, we knew how to get the optimal policy. So the optimal policy was argmax over action of R of x and a, which is equal to this expectation. That was the definition. So we are optimal policy is defined that way. So if you want to get optimal policy from V of pi, it might sound a bit less straightforward, but it is not. We can actually get it from that relatively easily. Okay, so we want to find a policy that among all possible policies has the highest value of V of pi. So let's search in the space of say all deterministic or stochastic policies. So if we denote the space of all stochastic policies by capital pi, so it would be the space of all distributions such that pi of dot condition on x belongs to space of distributions over actions. Remember, M of A means the space of distributions over actions. And this is defined for all states. So this is like, if I have 10 states, I have 10 distributions for each of states. If I have infinite number of states, I have infinite number of distributions for each x. And then I kind of combine all of them, and that gives me this pi, which is here. And this is the space of all possible pi's. So what we want to find is find a policy that if we search over all possible policies, the value function of that policy is as large as possible. So in the case that t is equal to 1, this is not difficult. Kind of the reasoning is like this, that the value of v pi at two different states, x1 and x2, they are not interacting with each other because they only go for one step. So whatever value we have at state x, x1, doesn't interact with the value at state x2. So we can kind of find the best policy by looking at the best policy condition on x1, best policy condition on x2. So hopefully this is more clear. Okay, so let's see, for each x equal to each x in the state space, v of pi can be defined, it's defined as, so this is the integral, or it's an expectation of the reward distribution, d of r condition on x and a, when the action is selected according to policy pi. So action is selected this way, and this is the states. And this would be the same as, so we take expectation, we get, this would be the expectation of expected reward. So this was the expectation of reward condition x and a, when I'm kind of taking expectation of it according to policy pi. So this is v of pi. So you see that it's kind of related to r of x and a that we had before, but it depends on the policy, how, the weight that the policy gives to each of the possible actions. So now if we want to find a policy pi that maximizes v pi, we can focus on each of the states and compute this maximizer or supremum. So supremum of our all possible past distributions that is defined for state x of this v of pi at x. So that's kind of the same as what we had in the previous slide. Like this is the same, but I'm just focusing on specific state x. So now I guess you need to think about it a little bit, but kind of the idea is here is that the maximizing distribution can concentrate all of its mass at the action that maximizes r of x and a. So assuming it exists. So therefore, the optimal policy at that point is the distribution. So this is a Dirac's delta notation. The distribution that puts all its mass at argmax of r of x and a. Or equivalently, instead of form of the distribution, we can define it in the form of function. So we say that it's a function, pi star of x, that chooses the action by choosing the maximizing action at that state. So this is for t equal to 1. And okay, so this, and if you recall, this is the same that we had before for the immediate reward maximization case. So if it is okay, I think since this is Zoom and not real classroom, I'll go ahead a few minutes more so to finish this lecture. And I mean, if you have to leave, that's okay. I'm recording this and we will post it somewhere. But let's finish the lecture. So here, this is we get optimal policy given v of pi. Okay, so that was a finite horizon task. Episodic task is the situation that I also described in the beginning, that the problem goes for t time steps, but t, we don't know what it is. So there's a final t that episode ends. So episode always ends, but it's not fixed a priori. So for example, in a game of chess, the game ends at some point, but it might be in, I don't know, 30 steps or 100 steps or something like that. Or for example, if you are in a maze, finding goal in the maze might take 20 steps or 100 steps. We don't know, but it ends at the end. Or a robot successfully picks an object, for example, or reaches an object. That's another example. Like we go until that point and then the episode ends. So we say that episode terminates whenever the agent reaches a certain state within the state space. So it's that state, we call it terminal state. So you can think of it in chess probably. It would be the state that one side checkmates the other side. So that would be the terminal state. Maybe it's more intuitive. Actually, instead of thinking of one single state, we think about a bunch of different states, like that ends the game or ends the episode. But again, I guess mathematically we can define only one single state, and everything that gets to any of those possible states that ends the game, just kind of collapse all of them into one single state and say that that's our terminal states. Okay, so I guess the other thing that is important here is that the length of episode T is a random variable because we don't know when it ends. So this is episodic task. The definition of return and value function is very similar to the previous case. So this is the definition of return. Here, the only difference is that T is a random variable. And the definition of value function is again the same as before. It's expectation of return condition on state X1 being one particular state. So I have some remark here. So it's kind of become a bit, when gamma is smaller than 1, so it's discounted case, then everything is very well defined. But if the gamma is equal to 1, then we have to be a bit more careful. The reason is that if gamma is equal to 1, and it happens that the episode never ends, like T is infinity. Like in the previous definition, I didn't say that T is a finite number. It's a random variable, it may never end in theory. In that case, if gamma is equal to 1, then the definition of return might not be well defined. Just imagine that all rewards are equal to 1. So we have 1, k equal to 1 to infinity. So this is not well defined. But on the other hand, if we had the k minus 1 here, this would be well defined because the value of it would be 1 minus gamma, which is, if gamma is between 0 and 1, that's finite. So we don't talk much about episodic case with gamma equal to 1 from the theoretical perspective. But when we want to study the theoretical properties of it, usually we have this extra condition that we somehow assume that the episode ends. So at some point it ends. So if it ends, it ends in a finite time. If it ends in a finite time, everything would be well defined. Okay. So then we get to this continuum task, which is the case that the interaction between the agent and its environment doesn't break to natural episodes that terminates. So it goes forever, essentially. So for example, if you have a lifelong robot, that would be a case of it. The other is that, say, if you have a chemical plant that is supposed to work for forever. So it's not like episodes of finite horizon of a month. It's supposed to go for a long time. Or maybe we sometimes think about continuum case, like forever as an approximation of a very large T. So if T is 1,000, it's almost like forever, like waiting for 1,000 months. It's a very long time. So we use this continuum task model as a model of very long horizon problems. So this is a continuum task is what most of our discussion will be about. And I mean, part of the reason is that it's mathematically a bit simpler, that is in some aspects. And it gives most of the intuition. But again, it might be just idealization. Okay, suppose, again, I define the return and everything. So here, consider sequence of rewards R1, R2 to R infinity that is generated when agent starts at state x1 equal to x and following policy pi, given a discount factor, which you notice that here I make sure that discount factor is smaller than 1. The return is defined this way. So here is a bit different notation. So I'm using g of pi and with subscript t. So this is essentially return after time step t. So here I'm saying that for k's that larger or equal to t, I compute, okay, so this should be, this is not correct. It should be gamma to the power of k minus t. So what, yeah. So that would be the instant. So here, this part was incorrect. So essentially, we want to talk about the return that we get after time step t moving forward. So that's the kind of the idea of return. And then we can define the value function. So it's defined very similar to the previous case. It is defined as expected return, but I just write it as a definition because this is a definition that we often use. So I defined it, and also another notation. So first we have pi. This is called value function or state value function. And also we define q pi, which is called action value function. So that's why sometimes people use state value function to differentiate from action value function. So what's the definition? So the definition, like v of pi, is as before. So this is the return that we get when state x1 is equal to x. So if we start from x1 equal to x, and then compute the return from that point up to infinity, take expectation of all possible runs of it, all possible episodes of it. I mean, episodes never end here. But if we take the expectation of it, that would be of v of x, v pi of x. So here, q, the definition of q is a bit different. So you see that we have x and a. So here, the condition is like this, that we take x1, we start from first state as x, but then at the first step, instead of choosing action according to policy, I choose action equal to action A. So this is first time step. I go to the second time step, and then after that point, I follow the policy. So v pi, we follow the policy from the first time step. Q pi, we follow the policy from the second time step. These would be the definition. And if we take computer return of it and take expectation, that would be the action value function q of pi. So yes, so let's reward is a sequence of reward, and the process is started from state x1 or x1a1 for the action value function, drawn from a positive probability distribution of states or xa. So this is kind of technical definition, so everything is well defined. Basically, the conditional expectation would be well defined. And then follow the policy pi for time t equal to 1, 2, and up to infinity. That's for v pi, or from t after t equal to 2 for action value function. Then we have these two definitions. Any question? Let's see if there is a question.
So X is always the initial state. both v pi x and q pi x, A, you are seeing that x1 equals to x, which means that x is the initial state.
Yes.
Which means that if we start from different initial state, then the Vx will be different. And
yes.
So it's very important for choose the initial state.
I guess your voice kind of broke a few times, but so V of x depends on initial state, which is x.
I see. That's my question. Thank you.
Right. Yeah. So it's a yes, exactly. Like this x initial state that we have appears here. So V of x1 might be different from V of x2. Is it good? Okay. So this is a continuing task, the value function for continuing task. So the important thing, the difference with what we had before is that the time goes to infinity. And we also have discounting in the definition. Okay, so yeah, value function v pi evaluated at state x is the expected discounted return of following the policy pi from state x. So I said that. It's good to repeat. The action value function q pi evaluated at state x and action A is the expected discounted return when the agent starts at state x, takes action A, and then follows policy pi, like after time step 2. So this is maybe one thing that might not be super clear to you is that why we have defined Q. Maybe there is a good reason for it. It makes some computation easier. But if we compare it with immediate reward maximization case, maybe you get a better intuition. So if gamma discount factor is equal to 0, we are effectively, well, the definition of Q would reduce to, so I guess we have X and A, we'd reduce to expectation of reward at first time step when X1 is X and A1 is A. So because gamma is 0, as long as we have gamma to the power of 1 or 2 or whatever, the value would be 0. So the reward R2 or R3 or any value after R1 would be ignored in the definition of Q. So we get this expectation. And this expectation, if you recall, is the same as the expected immediate reward that we had before. So in gamma equal to 0, this is the case as, this is the same as expected immediate reward. And also gamma equal to 0 is the case that the agent is very myopic. It is only looking at the first time step and ignores whatever happens afterwards, right? So this is somehow like the case of time horizon being t equal to 1, even though the problem is defined a bit differently. So when we had R of X and A, we could easily compute the optimal value function by taking argmax of R of XA. Here, the same way, when Q pi is the same as R, if we take argmax of Q of pi of states X and A, for the case of gamma equal to 0, we get the optimal value function. So this is essentially an easy way to compute the optimal value function, the same way that having R of X and A was easy, or makes it easy. When gamma is larger than 0, the argument is not the same, of course, but you will see that the result is the same if you, in some detail, of course, but we get to that later. Okay, let's talk a little bit about optimal policy and optimal value function. So what does it mean for an agent to act optimally? So first, think about the case that we want to compare two policies. When we say one policy is better than the other one, we say that one policy is better than other policies, say pi is better than pi prime, if the value of V of pi is always equal or larger than V of pi prime for all states in the state space. So based on this, the optimal policy would be a policy that satisfies this kind of relation in inequality, or satisfies this relation. So if it is better than any other policy, that's the optimal policy. And better means its value at all states is better than all other policy. So I guess and this policy, V pi, is called optimal policy. I talked about V pi star before in the case of t equal to 1, but here is kind of the more general definition, like it applies for any task. So I guess the comment here is that there might be more than one optimal policy, so it's not necessarily unique, but we usually refer it to as the optimal policy, even though it might be hundreds of them. Okay, so we have optimal policy. Now we can think about the idea is that optimal policy is a policy whose value is larger than any other value function, right? So this essentially means that we search in the space of all possible policies, all stationary Markov policies, and then find the one that has the maximum value. And that would be V star. So here we choose one of the maximizers in kind of like arbitrary way. So there might be more than it. And this value function, that value function of the optimal policy, is called the optimal value function. So optimal value function is V of pi star, which is sometimes we simply denote it by V of V star. So we don't have V pi star. We also can define the optimal policy based on Q pi. So we say that we search in the space of all possible policies and then find the one that has the maximum value for all states, kind of dominates other policies. And that would be the optimal action value function denoted by Q pi star or Q star. Okay, so as before, I guess for immediate reward maximization or finite horizon equal to t equal to 1, it was easy to find the optimal value function, or it is easy. So recall that pi star was like this. So pi star is argmax of R of X and A. So if we just substitute it to definition of V of pi, we get that V star optimal value function is, the value of it is maximum over actions of R of X and A. So maximization is over actions. So this is the optimal value function. And I guess it is clear that like V star optimal value function, which is this, is larger than R of X and pi X for any policy, equal or larger. So this is kind of satisfies our definition 2-3 slides ago that the optimal value function should have a value that is larger than any other policy. And so here, I guess my focus was on deterministic policies, but if we go to stochastic policies, the conclusion would be the same. Okay, so there are some questions. When we go to a continual task, or even finite horizon with t larger than 1, we can ask several important questions. One question is that whether there exists any optimal policy after all. We haven't proved that. So maybe there's no single policy that can dominate all others for all states. So it is imaginable that at best we can find a policy pi star, which is not necessarily not optimal policy in our definition, that is better than any other policy only on a subset of X. So instead of all state space, it's only better in the subset of it. So in that case, there's no optimal policy. The other question is that, if you remember, I focused on policies that are stationary, Markov and stationary policy. But maybe it is possible that we find a policy pi bar, that depends on time step, pi 1, pi 2, pi 3. And if we follow that policy, which means that at the first time step we follow pi1, second time step we follow, we choose action according to pi2, and so on and so forth, maybe the value of that policy is actually better than value of any stationary policy. So that's imaginable. And I guess, so we will talk about this later, but kind of the idea is that we will see that the optimal policy exists. So that's good. The first question is answered. So it exists. And also we can show that there exists an optimal policy that is a stationary policy. So I may try to prove it, but this is not like trivial. We need to prove it that this is the case. And I guess the other question is that how we find the optimal policy. So when the task is continual task or finite horizon, how we can do it. When t is equal to 1, it was easy. So we differentiate in two setups, and I think this is important. One is that how we find the optimal policy if we know the model, we know the MDP. So we know P and R, how to find it. So I call this the planning problem. The other is that, maybe more interesting, is we don't know P and R. So we only have data from it, like that agent interaction with the environment. We only have X's, XTs, and RTs, and ATs. But we don't know what is the process that generated that data. Maybe because it is very complicated. Like a patient's body is generating that data. We don't know what the P is, but it exists. But we only see the only thing we see is the data that is generated. That is called reinforcement learning problem. So I differentiate between this planning problem and reinforcement learning problem depending on whether we know the model or not. And as you see, many of the methods and ideas are very similar. Okay, so any questions so far? I know it's taking a long time, but I think it might be better to finish it then.
Amir-massoud, I've got a quick question about planning.
Sure, yes.
Is it required, my understanding is that planning is that you either know the reward function or the transition model. It's not requisite that you know both. Is that not true? Does planning require you to know the reward function?
Well, the way I define it here is when we know both of them. But I imagine that you can define it when the reward is known, but the model is not, P is not known, or vice versa. Also, I should say that different communities refer to a bit different thing as planning. Like there's a planning community, but here in the context of RL, I differentiate whether both R and P are known or just not known.
Okay, thanks.
Okay, so so it takes a while because I want to go through every step as close as possible, and we get build all the foundations. It takes a while before we get to the any learning algorithm. So I was thinking that maybe it's a good idea to see one of very famous reinforcement learning algorithms, which is called Q-learning. So I think it was introduced in '89 by Chris Watkins. And then, which is a kind of example of what Rich Sutton has done, like temporal difference learning. So it's a kind of, you can think of the variation of it. So this is a kind of very influential algorithm. There are also the variations of it that people have studied a lot. And I think it's kind of good to take a look at how it looks like. So this is Q-learning in kind of generic form of Q-learning. So we have a step size. So this is for finite, this to be meaningful or work actually. It works for finite state and action spaces. So here kind of the assumption is that X times A is a for it to have nice convergence properties. So we have a step size alpha. You'll see how it works. We initialize Q function. And this is, since this is finite, we can store it on some kind of lookup table. So we can store it on some way, and we can initialize arbitrary. Maybe initialize it 0 or some other value. So except that for terminal state, we know what terminal state is. We should initialize it equal to 0. So for terminal state, it should be initialized 0, elsewhere arbitrary. But in many cases, people initialize 0 anyway. So for each episode, so this formulation works for episodic case or continual case, or continuing case. If it is continuing case, there is no episode. So you go into this for loop once and you stay there. So, but in episodic case, you initialize x1 according to some distribution. So it's where your robot is put the first time step. And then you go for many steps. For each time step, agent choose action AT according to its policy, some policy. And then it takes action AT and then gives that action to the environment, gets the new state xt plus 1 and the reward. So we get the reward and then we update Q using this following update rule. So what is the update rule? Update rule says that the value function, action value function at state xt and AT should be changed like this. So we take the previous value, but add alpha times this bracket. So alpha was learning rate between 0 and 1. And this bracket is essentially, what is it? It is RT, rewards that we take at time step t, plus gamma, discount factor, times maximum of action value function at next time step. The maximum is over A primes, over all actions. So we have this Q, we go to the next state, we compute the maximum value of it, and then add it, multiply it by gamma and add it to reward. And then we subtract Q from it, the previous value of Q. And then we update RQ. And then we go to the next time step until the end of episode, for example. Or if it is continual task, we go forever. So this is Q learning. I mean, I guess the only part that is different from, I mean, you have seen all steps in the generic interaction of agent. The only part that is new is this update rule, right? So it takes a while before we understand what it means. I think probably the 4th lecture, if we remain on time. But that's it. Okay, so I haven't talked about how pi should be selected. There are different ways that pi can be selected, and that's actually one of the benefits of Q learning. We can work with a variety of pi's, and we always, and in all cases it works. But the common way that it's used is called epsilon greedy policy. So what is epsilon greedy policy? At 8, when we are at time step t, and we get xt, with probability of 1 minus epsilon, we choose action that maximizes the Q of xt and a. And with some other probability of epsilon, we choose another action. So think of epsilon as a small value, so it's 0.1. So with 90%, we choose the maximizing action. With 10%, we choose a random action. And random action might be uniform or any other distribution. Here I've just wrote it as uniform distribution. So what is kind of interesting about Q learning is that under some certain conditions, we can show that Q learning algorithm converges to Q star, like the QT, the Q that it computes and updates, it converges to Q star. And so that's interesting because if you have Q star, we can all easily get the optimal policy from it. I think, okay, any question? That would be this is the last technical slide of today. The rest would be logistics. Okay, let's go to logistics. Okay, so there is a course webpage. I think I've sent the link of it in the first announcement on Quarkus. The information will be basically updated there mostly. Like I put slides and lecture notes there. Use Quarkus for announcements and grades, and we will use Piazza for discussions. I haven't set it up yet, but I will do it soon. What else? So lectures will be delivered like this, synchronous via Zoom. I will record it and share it. I'm not sure what platform, like I should see how it works. Hopefully it's been recorded, but maybe YouTube. But we will see, I will announce that. If you have any kind of suggestion or objection, let me know. Okay, so you can download recorded lectures for your personal academic use, but don't share it. I mean, of course, if it is on YouTube, then everyone can see it, so that doesn't matter. But sure. Yes. Okay, so I guess not. So during lectures, I mean, keep yourself on mute. You have done that very nicely today. Unless, but when you have a question, just ask. And then there are some forms, like if you get sick, what you have to do. So there's a link there. If you need some kind of academic accommodation, there's a procedure for it. I guess you have the accessibility services can help. And based on what they provide, I mean, I might give you kind of more accommodation, say for your homework assignments, a few more days or something like that. Also, I realize that this is kind of not a usual time, so I try to be as accommodating as possible. Probably not that you can always send your homework late, but if it's a bit late, so there's an issue, I guess we can discuss it. So just send me an email. And for email, I guess there will be a course email so that I can filter it easily. I will announce it. But for now, I mean, you can send it to my email address. Okay, so course evaluation. This is a bit tentative, so it would be finalized soon, but to give you an idea what components you have. You have 3 homework assignments. Each of them would be 15%, so 45% total. And it would be kind of combination of mathematical derivations, proofs, and kind of programming exercises. Programming exercises is supposed to be basically give you some chance to practice RL algorithms on some simple domains. So they are not supposed to be very difficult, but it requires you to do some coding. But then a big part of it would be kind of derivations or proofs, probably similar to what you have in the lectures, but maybe for a slightly different setting. So there is a research project. Tentatively, it would be 30%. So the idea is that you write a research proposal on a research topic, and then you have to write a report on it in addition to a proposal, and then you have a class presentation. What I'm thinking is that we do some peer reviewing, like have a kind of mini conference that you submit to some website, and then you review other papers by other students. So it is mostly like a kind of experience of how a conference would be. I don't think we have any reject or accept, you just get comments. But this part depends on whether, like, this peer reviewing part depends on how difficult it is to set up with the number of TAs that we have. So there would be I'm thinking of having some kind of take-home exam, which basically help you to think about some material in a serious way for 2-3 hours. So it would be closer to the end of the course, probably. Yeah, so, but it would be something between usual midterm time and final time. It wouldn't be during the final times. And then, so the other thing that probably we will do is that read some kind of papers, classic papers, and then write a summary of them. So maybe 5 or 10 papers, you read it. So you get also some idea about topics that I can't cover during the lectures, but it's good to know. So also it's a good experience to read some research papers, and especially if you've just started your grad school and you don't have much experience in doing that. So the amount, whether it's 10% or not, is not clear. Then I was thinking of some bonus points. So this is again tentative, but I'm writing some lecture notes for this course. So it would be a kind of mini textbook or something like that. And my idea is that if you find an error in it or a typo in it, the first person who tells me about that gets a bonus, say 1% or something like that. Active class participation, I don't know how to evaluate it, but that's a good idea. So maybe it is not part of the bonus point, maybe it is. But active class participation is a good idea anyway. Okay, so collaboration assignments. Collaboration on assignments is not allowed. You have to do it yourself. But for projects, you need to build a team of 2 or 3 members. And the exact number of members of a team depends on how many students we end up having. Like if we have a lot of students, probably we have a larger team size. Okay, then we have a submission, late submission for any part, like homework assignments, proposal, anything. So there would be a penalty per day, like say 10%, for example, up to a few points, up to a few days, like 3 days. If after that, like a week after that, we can't accept it, unless there is a good reason, like if we discussed it before, we can do it. And kind of the reason is that TAs can do it once. We can't grade at different time points. Yeah, I guess extension can be granted in special cases. Okay, that's good. Okay, so these are not references for, it was references for the Q-learning and temporal difference, not the references for the book, for the whole course. I will send some good books to read in addition to the lecture notes that I provide. I mean, one of them would be Sutton and Bartow's Introduction to Reinforcement Learning. That's a very good textbook. It covers a lot of material. It's very intuitive, so it's good to read. But sometimes it is less mathematical than my coverage of some material. But also it has some material that I'm not going to cover much. There is also Chaba-Sepeshwari's Algorithm for Reinforcement Learning. That's a good book. And there are a few others that I will post on the website. I think that's all. Yeah. Okay, so any questions, comments